Okay, so this video is actually going to cover the content of two sections. Section 8.3, which describes why do chemical reactions occur, and section 8.4, which is concerned about types of chemical equations. So chemical reactions occur because the arrangement of atoms and the distribution of the electrons within those atoms in the products is more stable than the arrangement of atoms in the reactants. So basically a bunch of molecules or atoms collide with one another and they're like, hey guys, you know what? We could organize things that would be better. Let's kind of like rearrange how we're like interacting with one another and come to a more stable arrangement. And that's what happens, right? So that's the driving force for a chemical reaction. Now, there are a lot of indications that a chemical reaction has occurred, and some of these are, very well recognized by chemists. So these include formation of a solid, or what chemists call precipitation reactions. We also might see formation of a gas, and this is generally indicated by bubbling. So it'll look fizzy, kind of like soda water. Or we might see what we call formation of water. These are sometimes referred to as condensation reactions because we're making water, but there are other types of reactions that form water, including acid-base reactions and a class of reactions that we're going to look at called combustion reactions. There's a very special class of reactions called redox reactions that involve the transfer of electrons. And in these reactions, what we'll often see is that metals will lose electrons and form ions, and non-metals will gain electrons and form ions. So these kinds of reactions are often indicated because the metal will fall apart, right? So it's very, very obvious if this is occurring. So a chemical reaction is a process that results in at least one new substance being produced. So if you don't get a new substance being produced, it's not a chemical reaction. It could be a physical change. So there are five important classes of chemical reaction that we're going to look at. The first two are pretty easy to recognize. The first one is a synthesis, or sometimes referred to as a combination reaction. You can recognize this guy because it's like multiple things come together to form something else. The second class of reaction that I said that's pretty easy to recognize is a decomposition reaction. And you can recognize this fairly easy because it's just like one thing that breaks apart into multiple other things. The last three reactions here are a little more difficult to recognize. We have to dive a little bit deeper into the nature of the products and the reactants to recognize them, but we're going to show you how to do that. These are single replacement reactions, double replacement reactions, and combustion reactions. Now, how you're going to be able to tell what class of chemical reaction you're dealing with is by looking at the nature of the reactants and the nature of the products, and you'll be able to tell what kind of reaction it is. So, as I said before, a synthesis or combination reaction occurs when multiple reactants combine to form a single product. Now, if we're going to combine multiple different things into the one thing, that single product must be a compound. It can't ever be an element. So a synthesis reaction could occur between multiple elements, but it'll always form a single compound. But it also could occur between multiple compounds, but again, it's only going to form a single product. And it could also occur between a compound and an element. The key thing is that a synthesis reaction is multiple reactants combining to form a single product. Okay, a decomposition reaction is kind of like the opposite of a synthesis or combination reaction. In a decomposition reaction, you have a single reactant which is always a compound, and it breaks apart into multiple things. Now, the things that it breaks apart into could be elements, could be compounds. But the important thing is that our reactant is always a compound, and there's only one reactant, and that reactant breaks apart to form multiple products. So again, this one here is pretty easy to recognize. It's basically the opposite of your synthesis reaction. Okay. Now, a single replacement reaction is a little more difficult. In a single replacement reaction, what happens is an element replaces another element in a compound to form a new compound and a new element. So it's always like this. It's element reacts with compound to form new element and a new compound. And that's how we're going to recognize a single replacement reaction. All right? So you can see here, element plus compound, and the iron is going to replace the copper. So now we've got new compound, new element. So here we go, element with compound, and you guessed it, the aluminum is going to replace the iron, and now we've got new compound and new element. All right, element and compound, element replaces a different element in a compound to form new compound and new element. So single replacement reactions always have two reactants, which are an element and a compound, and they always have two products, which are a different element and a different compound. So again, you just got to know how to recognize them, and you'll be good. So a double replacement reaction occurs between two compounds, and what happens here is that they kind of exchange parts. They flip partners, right? So we have compound 1 reacting with compound 2, and they're going to swap parts. And what we're left with is compound 3 and compound 4. So two compounds react to form two new compounds by exchanging parts. So here we go, silver is going to exchange for sodium to form two new compounds. Potassium is going to exchange for the lead. We're going to flip partners to form two new compounds. So exchange reactions involve partner switching, right? They're going to change components, and they're going to form two compounds. They're going to form two new compounds. All right. So there's a common type of double replacement reaction that I did mention previously. It's called an acid-base reaction. And an acid, is a compound that contains hydrogen, and its formula will begin with hydrogen. And then a base is a class of compound known as metal hydroxide. So they are ionic compounds that contain the hydroxide anion. And this reaction always results in the formation of water and an ionic compound. An ionic compound is commonly referred to as a salt. So people will memorize an acid-base reaction is the following. It's an acid plus a base gives a salt and water. So here it is here, hydrochloric acid reacts with the metal hydroxide, the base sodium hydroxide, and what happens is that they exchange partners. So the hydrogen exchanges with the sodium, and we form sodium chloride and H2O, right? Because the H combines with the OH. Here's another one here. Two hydrogens exchange places with two sodiums, forming sodium sulfate and two waters. So this is the salt, and this is the water. This is the salt, this is the water. Here's another one. Two hydrogens exchange places with one barium. We end up with the ionic compound, barium fluoride, and two amounts of water. All right, so there we go. All right, so that's how this works. All right, so acid-base reaction can be a little bit hard to follow, but if you to spot, but you've got an acid reacting with a base, it always forms water and an ionic compound. It's not too difficult once you get in the groove. So our final class of reaction was a combustion reaction. And in a combustion reaction, what happens is a substance reacts with oxygen to form some kind of oxide. So carbon dioxide, right? Carbon monoxide, yeah, sulfur dioxide. But it always combines to form an oxygen-containing compound called an oxide. And combustion reactions are accompanied by the release or the evolution of heat and light. So you can see in this combustion reaction, we know it got hot because the water is present as steam. So this is a classic combustion reaction, the combustion of methane. Methane is natural gas, so if you have any gas appliances at home, the gas being piped into your house is mostly methane. So we've got CH4 gas reacts with O2 gas. That tells us that this is a combustion reaction to form carbon dioxide. There's our oxide and water, right? Now, hydrocarbons are compounds that contain only carbon and hydrogen, and whenever they undergo combustion, the products are always carbon dioxide and water. Now, if you burn a non-hydrocarbon compound, so for example H2S, hydrogen sulfide, that's a rotten egg gas, smells nasty, smells like rotten eggs, you don't get carbon dioxide. In this case, you get sulfur dioxide. So you can see though as well that it does result in the formation of a bunch of heat because the water is present as a gas. Again, what's happening here is, it's you can't really. What we can see here is that we've got an element and a compound reacting, but they're not forming a new element and a new compound, so we know that it's not single displacement. So you don't want to confuse this with single displacement. So we do have element and compound, but it's not making a new element and a new compound, it's making two new compounds. Alright, so really you just have to have a checklist of these things, and then you can recognize them on the basis of what the reactants are and what the products are. So let's have a look at some of these guys here. So it says identifying combination, decomposition, single and double displacement reactions. So I know none of them are going to be combustion, all right? So combination is multiple things combining to form a single thing. And that's the first one, isn't it? Because we've only got one product, right? Two reactants, one product. Decomposition is one thing, one reactant breaking apart into multiple products. And looks like we've got two of those. There you go. So both of those guys there are decomposition. They're both decomp reactions. Okay, so that's pretty good. Alright, now we're going to look at precipitation reactions, combustion reactions, and acid-base reactions. So precipitation means that a solid forms. I mentioned that way back. So what ones of these result in a solid forming? There we go. Oh, this results in a solid forming. And this results in a solid forming. Now, the other thing to remember is that these can be other classes, because it says check that all that apply. Other things are happening as well here. So precipitation just means that a solid forms, but it's not really classifying whether it's a single replacement, whether it's a double replacement, whether it's a decomposition, whether it's, it's not whether it's an acid base, whether it's a combustion. So let's check, are any of these, now we've done that bit, combustion reactions? Do any of them involve oxygen? This one, woohoo, Okay, so sodium reacts with oxygen to form sodium oxide. So that is definitely a combustion reaction. Right? Okay. Alright, so we want to keep that in mind. Now, something else that I'm noticing here is this is also a combination reaction. Multiple things combining to form the one substance. So that's also a combination reaction. So we want to be careful there, right? That we get all of the things that apply. All of the things that apply. Okay, so we've got combustion out of the way. And now, what about acid-base reactions? Well, no hydrogen's there, so it can't be acid-base. No hydrogen at all here, so it can't be acid-base. No hydrogen here, so it can't be acid-base. No hydrogen here, so it can't be acid-base. But there are many other things to check as well, aren't there? We've checked precipitation, combustion, acid-base, but it also looks like we have to check for combination. We also have to check for single replacement, and we also have to check for double replacement and decomposition. So decomposition is when we have one reactant. So let's check for any of those ones. 2 reactants, 1, 2, 2 reactants, 1, 2, 2 reactants, 1 reactant. So that is decomposition. So we've done decomp. Okay. Combination is where we have just the one product, and we've already detected that. So 2 products, it's not combination. 2 products is not combination. 2 products is not combination. 1 product, it's combination. So we checked for that. Single replacement is where we have an element reacting with a compound to form a new element and new compound. So 2 compounds, so it's not single replacement. Element plus an element, so it's not single replacement. 2 compounds, it's not single replacement. Single compound, it's not single replacement. So none of them are single replacement. Double replacement is where we have 2 compounds that exchange partners. So it looks like that's what happened here. The sodium and the iron switched places. So that is a double replacement. Okay, here 2 elements, so it can't be double replacement. Here we have 2 compounds, and yep, it looks like they switched partners. Yep, so this one here, double replacement. Oh, I missed it. It also forms a solid, so it's a precipitation reaction. Okay. And then here, only the 1 compound, so it can't be double replacement. So we checked everything, all right? So we had to go through and check all of these things here. There was a total of 7 things, and so we just have to go through and check them all. And you can see it was really easy to miss some of these, so be systematic with this. Okay. All right, it says predicting products from a general statement about reactivity. Over sushi and sake at dinner one night, your friend Hong, an expert chemist, says this: did you know all alkali metals, so alkali metals are group 1A, and halogens are group 7A, combine to form halides. So halides would be things like fluorides, chlorides, bromides, iodides. It says, using Hong's statement and what you already know about chemistry, predict the reactants of the following reaction. Be sure your chemical equation is balanced. So we're going to react an alkali metal, which in this case is going to be sodium, and sodium is not a diatomic element, but it's a solid at room temperature. Right? There we go. We're going to react that with the halogen chlorine. And chlorine is a diatomic element, and it's present as a gas at room temperature. And those two things are going to react to make solid sodium chloride, which is our halide. Now, it doesn't quite balance because we've got 2 chlorines on the left here, and only 1 on the right, so I'm going to have to put a 2 there, and then that's going to mess with my sodiums, so I'll need a 2 there. So my balanced equation, taking into account everything I've learned so far, looks like that. And I know the ionic compound has to be a solid because ionic compounds are all solids at room temperature, and we were told it was in this case. So there it is. 2 sodiums on the left, 2 sodiums on the right, 2 chlorines on the left, 2 chlorines on the right. Not too bad. Okay, so that concludes this short video that works through sections 8.3 and 8.4. Hope you found it helpful.